and then we have 4 plus 1 by n plus 2n, where n is taken common from each of this, this and this. Therefore, when n is taken common, n times n is n cube, and this n taken out brings 2 plus 1 by n, 4 plus 1 by n plus this. Now, when I take the bracket in, I get limit n tending to infinity of this multiplied with this, cube get cancelled, and I get 1 by 3 times 2 plus 1 by n, 4 plus 1 by n, and then I get 2 by n square when n cube is taken in and each of the terms get cancelled, and finally I get this plus this. Now next, I have n tending to infinity implies 1 by n tends to 0, because we have the property that when n tends to infinity, 1 by n tends to 0, simply because 1 by infinity is defined as 0. So using that, let's see what this further modifies to. That is, when I take this, each of n tending to infinity implies 1 by n tends to 0. Therefore, each of 1 by n is substituted with 0 here. And not only that 1 by n tends to 0, even I have 1 by n square also tends to 0 for n tending to infinity. Now, as we see here, this n taken inside reduces this into the form 1 by 3, because n times of n square is n cube and all n gets cancelled, and 2 plus 1 by n, 4 plus 1 by n plus 2, because this n gets cancelled with this. And therefore, finally, I get this to be limit n tending to infinity of this, and we have when n tends to infinity, clearly 1 by n tends to 0, or even 1 by n square tends to 0, etc. And we have 1 by infinity is always 0, and therefore n tends to infinity implies 1 by n tends to 0. So we use this condition out here and here, so that we get when limit n tending to infinity substituted in place of n reduces this to integral 0 to 2 of x squared plus 1 dx will be 1/3 of 2 plus 1 by n is 0 when n tends to infinity. Therefore, I get this as 2 plus 0 and 4 plus 0 plus 2 is what we get. Now, this on further simplification gives 1 times 2 times 4 plus 2, which is 8 by 3 plus 2, and therefore, this on LCM gives 3 to 6, 12, 14 by 3, which is the answer. That means when I simplify the definite integral 0 to 2 for the function x squared plus 1 dx, I get a constant or a fixed value 14 over 3. Therefore, integral of 0 to 2 x squared plus 1 dx, which is a definite integral, has a definite or constant value 14 by 3, which is obtained using the limit of a sum. Definite integral using the limit of a sum for the function x squared plus 1 dx at the bound 0 to 2 is 14 over 3. Now, definite integral also helps in finding areas under the curves. Finding areas under the curves is done using definite integral. That is, if I have x-axis, y-axis and origin, and say I have a curve which is given with the function y equals f of x, and there are two bounds, the lower limit, the lower bound being x equal to a and the upper bound being x equal to b, then area under the curve using these two bounds x equal to a and x equal to b is calculated using definite integrals. So finding area under the curve is strictly related with the definite integral. That is, this area under the curve is nothing but given by the shaded region, this, which is nothing but given by definite integral lower limit a and the upper limit b, are the bounds of a and b of the curve which is f of x dx. So area is connected with definite integral using the limits a and b. Is how we understand the area under the curve connected with the definite integral. Now let's see the most important theorem in integral calculus called the fundamental theorem of integral calculus. Now, what do we mean by fundamental theorem of integral calculus, and which helps a lot in solving many definite integral problems? One of the most significant is solving the definite integral problems using the fundamental theorem of integral calculus. So the fundamental theorem says that if f is integrable in closed interval AB, and if there exists a differentiable function f in the same closed interval AB such that f dash is f, or f is called primitive of capital F. Then in this case we say integral a to b, the definite integral of f of x dx, is given by the formula f of b minus f of a. Is how we define the fundamental theorem of integral calculus, which is connected with integrability of f and differentiability of capital F in the closed interval AB. Then we say f dash is capital F, then f is called primitive of f, and we have integral a to b f of x dx is f of b minus f of a. Now next comes the notation which we have for fundamental theorem of integral calculus. As we have seen that the fundamental theorem of integral calculus derives integral a to b f of x dx as f of b minus f of a, which is nothing but written as the function f of x with a to b. is how we write this in general notation. That means f of x from a to b is also defined as f of b minus f of a. Is what we define using the fundamental theorem of integral calculus with its respective notation. Next is the significance of fundamental theorem of integral calculus. So, in what way is the fundamental theorem of integral calculus useful in the math life? The significance. So, as we see that the fundamental theorem of integral calculus defines the definite integral a to b f of x dx as f of b minus f of a, where f is f dash, then it clearly shows that the significance of fundamental theorem of integral calculus is to integrate to find the definite integrals of the functions, to find the definite integral of the bounded functions, of course, is how we find the significance of integral theorem of fundamental theorem of integral calculus, which helps in finding the definite integrals of the functions. Definite integral f of x dx from a to b is found by just finding f of b and f of a and subtracting as f of b minus f of a, where f is small f dash. So, next is the properties. Now that we have defined the definite integral using the fundamental theorem of integral calculus, next comes on the properties using the definite integral. So, we have three basic properties which we use in definite integral. The first important property is when I have integral a to b f of x dx, I can reverse the order. That is, if I reverse the order of limits as b to a, then it changes by sign. The reversing of the limits changes the sign of the function. Therefore, integral a to b f of x dx is minus integral a to b f of x dx, is how we understand the first property. Next, if the limit is itself, that is, if the lower limit coincides with upper limit for any function f of x dx, then that definite integral will always be 0 if the lower and upper limit match or equal, then this will be equal to 0. Integral a to c of f of x dx will be, if suppose I assume that there is a value b lying between a and c, then I can split this as a to b f of x dx plus integral b to c of f of x dx for b lying between a and c, is how we understand the third property. That is, if the definite integral breaks at b, then a to c is split as a to b plus b to c, as a to b and b to c is one of the property in definite integrals. So, these are the three basic properties which we use in definite integral in order to solve few of the problems with their respective properties. Now, let us see some example problems related to the definite integral, which is evaluated using the fundamental theorem of integral calculus. So, the topic is about the related problems. Say, for example, I take an example problem, integral of -1 to 2 of 1 by x square minus 3 dx. And then I would like to evaluate this definite integral using the fundamental theorem of integral calculus. So let's see how we can do this. Now, as we know that this kind of problem can easily be done if you are thorough with the indefinite integrals. Assuming the indefinite integrals, we have the only difference being that we have the limits lower and upper limit, but the rest of the integration is as similar as we have done for the indefinite integral. That is, this integral as sum of two terms is split as integral of each of the term minus 1 to 2 of 1 by x squared dx minus 1 to 2 of 3 dx is what we get when we split the terms. Then this can be further reduced as minus 1 to 2 of 1 by x squared, which is x power minus 2, and a constant which comes out, and then I get this. So once we modify, we reduce this into the standard form, because we have the standard formula for integral which say that integral x power n dx is x power n plus 1 by n plus 1, of course, plus c. So here n is minus 2, and therefore I get x power n plus 1 by n plus 1. But because I have limits, I use the notation with brackets, assuming that the limits are from minus 1 to 2. Is how we just write minus 1 to 2 of the integrated function. Similarly, I have this minus 3 integral dx we know as x, but this is bounded with the two limits minus 1 and 2, and therefore I get the brackets with minus 1, 2. Is how we understand the definite integral. The indefinite integral bounded with limits gives me next. This is x power minus 1 by minus 1, that is minus 1 by x, which I get when I simplify this, of minus 1 to 2 minus 3 of x minus 1 to 2 is what we get when we further simplify this. Now, it is our duty to substitute the upper limit first and the lower limit next. Therefore, minus 1 by x of minus 1 to 2 is understood as initially substituting with upper limit minus of lower limit. The first value of x is upper limit, which is substituted here, which gives minus 1 by 2 minus the lower limit, which is minus 1 by x is minus 1. And similarly, 3 times of upper limit, which is substituted here, and then the lower limit next, which is substituted out here. So this is the practice in solving the definite integrals, where upper limit minus lower limit is how we understand. So this on further simplification gives of minus 1 minus 3 to 6 minus 3, and therefore this will be minus 2, 6, 7, 8, 9 minus 10 minus 20 minus 1, which is minus 21 by 2. Therefore, integral minus 1 to 2 of 1 by x squared minus 3 dx is negative 21 over 2 is how we understand the definite integral using the fundamental theorem of integral calculus. Upper limit minus lower limit, and then we get the answer. Now let's see the properties of definite integral. That is, as we have integral a to b of f of x plus or minus g of x dx, then the definite integral of this can be split easily as integral a to b f of x dx So here the linear property holds clearly even for definite integrals, as can be clearly seen out here. Now similarly, if I have a constant attached to the function with limits a to b, then even for a definite integral, the constant can be taken out. Is how we understand the definite integrals. The properties of linear property and scalar multiplication property very much hold even in case of definite integrals. Now let's see the topic on using substitution, finding integral using the substitution. So a definite integral, just like the indefinite integral, also has some substitutions to be made. Therefore, equally the substitution has its limits equally changing. Say for example, I have to find integral 0 to pi by 4 of dx. So we have this as the substitution, or 0 to 1 of tan inverse x by 1 plus x squared dx. In order to evaluate this definite integral for the function tan inverse x by 1 plus x squared dx, we don't have the direct standard formula, but we try to use some substitutions. So let's see how the substitution helps. I assume tan inverse x equals some u. Then differentiating on both sides, d by dx of tan inverse x is 1 by 1 plus x squared dx is du. And this very much helps because this can be substituted with du on the right hand side. But in this case of definite integral, I have the lower limit which is 0 and the upper limit which is 1. Therefore, once I substitute this equal to u, all the terms, the variables x transformed into u, equally transforms the limits of x into limits of u. So let's find the lower and upper limit for the variable u. So as I take the lower limit of x, which is 0, so when substituted, respectively gives the corresponding lower limit of u when I substitute in the function this. So x equal to 0 implies u would be tan inverse 0, which is 0. So this is identified as the lower limit of u. Similarly, the upper limit x when substituted in the value of u gives us tan inverse 1, which is pi by 4, which is called the upper limit of the function f of u. So this is how we transform the lower and upper limits into the lower and upper limits of u as taken from x, substituted in the substituted function, and then we get this whole of the indefinite integral transformed into x running from 0 to 1, but here u running from 0 to pi by 4 of tan inverse x, which is u, and 1 by 1 plus x squared dx, which is du. And this clearly we know is integral x dx, which is x power n plus 1 by n plus 1, which is u square by 2 with the limits 0 to pi by 4. Next is substituting the upper limit minus the lower limit. So 1 by 2 taken common, u square is upper limit whole square minus lower limit whole square is what we get when substituted, this reduces to 1 by 2 of pi square by 16 minus 0, which is pi square by 16. This is nothing but pi square by 16 times 2, which is 32. And therefore, integral 0 to 1 tan inverse x by 1 plus x square dx is pi square by 32. This is how we identify the definite integral value using the substitutions called substitutions method. Next, the property of definite integral here is that if I have integral a to b f of x dx can also be simplified as integral a to b f of a plus b minus x dx. That's how we understand the integration of a to b f of x dx is integral a to b f of a plus b minus x dx. Therefore, now that we had the property integral a to b f of x dx is integral a to b f of a plus b minus x dx. If suppose I have to find integral 0 to a f of x dx in this form, then this would be integral 0 to a f of 0 plus a minus x dx by substituting each of this as lower limit and this as upper limit in case of this formula. It implies integral 0 to a f of x dx is integral 0 to a f of a minus dx. So we assume 0 to a f of x dx as 0 to a f of a minus x dx. Next, if I have to find integral of minus a to a f of x dx, then we have two formulae for this. That is, when f an odd function and when f is an even function. In each of the cases of odd function and even function, integral minus a to a f of x dx is said to be 0, and here it is said to be 2 times integral 0 to a f of x dx. So this is equal to 0 if f is an odd function, and this is equal to this if f is an even function. As we recap, the odd function is a function where f of minus x is minus f of x. F is said to be an even function if f of minus x is equal to f of x. That's how we understand the odd and even function. Odd function and even function derive this equal to 0 if f is odd and this equal to this if f is even function. This is the formula we use in case of odd and even function. Now you have two properties here for which I evaluate integral 0 to 2a f of x dx. So let's see the two basic properties. Integral 0 to 2a of f of x dx is 2 times of integral 0 to a f of x dx if f of 2a minus x is equal to f of x. But integral 0 to 2a of f of x dx is 0 if is this. So using these two properties, this is 2 times of this if this is plus of this, and this is 0 if this is minus of f of x, is how we identify the two cases for finding or evaluating integral 0 to 2a f of x dx. Now let's see the integrability of the product. That is, if f and g are integrable, is the product integrable, is the biggest question. F is integrable, g is integrable, implies we have the property that f g is also integrable, or gf, which we have, is also integrable, is how we understand the property of integrability of the product of two functions f and g. F is integrable, g is integrable, implies fg or gf is also integrable. Now that we have defined the integrability of the product, the immediate question which strikes the mind is integration by parts. As that we have seen for the indefinite integral, integration by parts is with its specific formula. Let's see how we can identify the integration by parts for a definite integral, which contains the lower and the upper limit bounds. So integration by parts for definite integral. So for definite integral, equally, let's see how it comes. Integral of uv dx, if I assume the first function as u and v, we have directly first function integral of second minus integral derivative of first into integral of second. This is how we understand the integration by parts for indefinite integral. But when we come to the definite integral a to b of uv dx, it is equally the same. Wherever I have three integrals here, I have the limits a to b out there. U integral a to b v dx minus integral a to b of u dash integral v of dx is how we identify the integration by parts for a definite integral, is what we get when we integrate by parts using the limits low limit a and upper limit b is to each of the integrals. Now let's see one example problem to support integration by parts for a definite integral. So for example, I have to evaluate integral of x e power x dx with limits from -1 to 2. So in order to integrate this, we use the first function and the second function, where this is algebraic and exponential, and using a comes first and e comes next, and therefore we get x times e power x dx where the first function is this and the second function is this. And expanding using the integration by parts, I have first function into integral of second minus integral derivative of first into integral of second is what we get. So expanding by that, I have the first function into integral of second function, but not to forget the limits, minus integral derivative of first into integral of second with limits this of dx is what we get. Now next, expanding by this, integral e power x is e power x with limits minus 1 to 2 using the standard formula of integral e power x. Derivative of x dash is 1 because d by dx of x is 1, and integral e power x is e power x dx is what we get. E power x with limits minus 1 to 2 minus integral e power x, which is e power x with limits minus 1 to 2. So we have this as integral e power x using the standard formula as this, with not to forget using the limits. Now next comes in substitution of the limits minus 1 to 2. So I have this with minus 1 and 2 overall with the function. So I have this minus 1 to 2, upper limit is 2 times e square minus minus 1 e power minus 1. So each of upper limit minus the lower limit, which we get, minus the upper limit minus the lower limit is what we get when we simplify using minus 1 and 2 in the substituted formula. This on further simplification gives 2e square minus of minus plus 1 by e minus e square plus 1 by e. 2e square minus e square is e square plus 2 by e, or you can just leave the answer here, or you can simplify with LCM, which gives e cube plus 2 by e. Therefore, integral minus 1 to 2 of x e power x dx is e cube plus 2 by e. Is how we identify the property of definite integrals connected with integration by parts. So integral of minus 1 to 2 x e power x dx is e cube plus 2 by e, where e is an exponential value, or e lies is an irrational number lying between 2 and 3, and e has approximate of value of 2.713. Just like pi is 3.14, e has an approximate value of 2.713, an exponential. Now next is the reduction formulae. As we have seen in indefinite integrals, we are going to discuss about the reduction formulae for definite integrals.